Hello everyone and welcome to another Würth Elektronik ISOS webinar. My name is Markus Eberle and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is Currently Under Pressure, discover our new MEMS pressure sensors. Our speaker today is Ninad Mehta, who is working as product engineer in the field of sensor components at Würth Elektronik ISOS. He will hold today's webinar and also answer your questions. As we also take all possible steps against the coronavirus, we are unfortunately not sitting in the same rooms today, but we are holding the webinar out of the home office. In case of technical problems, please take this into account. We will do our best to make a smooth process possible. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You will find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If you are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at isos-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. You can also watch the recording of today's webinar later on our website under the navigation point Webinars or on our Würth Elektronik YouTube channel. Now I will hand over to our speaker Ninad, and I wish you an exciting webinar.
Thank you, Marcus, very much, and a very warm welcome, everyone, and a good afternoon, everyone who have joined the webinar. The topic of today's webinar is Currently Under Pressure, discover our new MEMS-based pressure sensors. Let's have a look at the agenda. What I will talk about today. First, I will start with the introduction to the pressure, what is pressure, the pressure sensing technology. The focus of today's webinar will be MEMS-based pressure sensor technology. They will be explained in details, and then I will introduce to the absolute and digital pressure sensors from Würth Elektronik ISOS and some of their applications. Some of the applications include indoor floor navigation and HVAC. And at the end, I will conclude the webinar with the support what we provide apart from the sensors. So, what is pressure? Everyone must be aware of the definition of the pressure. So 1 Newton of the force applied on an area of 1 meter square will exert a pressure of 1 Pascal, which is equivalent to 0.01 millibar. All of the pressure sensors basically work on the same principle, where there is a thin membrane with a defined area which is exposed to an external pressure, and the pressure is measured. There are various types of pressure as well. For example, the air being a compressed medium exerts a force on the surface of the earth, which leads to an atmospheric pressure. The atmospheric pressure is different depending on your place, weather, and temperature. Another is the absolute vacuum, which is no pressure or 0 bar. When you measure a pressure with respect to absolute vacuum, this is considered as absolute pressure. For example, when I measure an atmospheric pressure of 996 millibar, it is an absolute pressure because it is measured with respect to the vacuum. The next is the gauge pressure. The gauge pressure is the pressure measured relative to the atmospheric pressure. The gauge pressure can either be positive for the pressure those you measure above the atmospheric pressure and negative for the pressure that you measure below the atmospheric pressure. At the atmospheric pressure, the gauge pressure is 0. The last one is the differential pressure. The differential pressure is nothing but the pressure difference between the 2 points. So basically a negative or a positive gauge pressure can also be considered as a differential pressure. Moving forward, we will have a look at some of the pressure sensor technologies. So the pressure sensors basically contains a mechanism or a structure that reacts proportionally to the force applied to a constant area of the surface. This is then converted into an equivalent electrical signal. There are various technologies being implemented in order to fabricate the pressure sensors. First one being the optical sensor technology, where the most common is the Farby-Perot interferometer, where there are two parallel reflecting surfaces are constructed at the end of an optical fiber. The reflective membrane at the end is subjected to an external pressure. Whenever the pressure is exerted on this surface, a phase shift is seen between the reference plane and the reflective membrane. The phase shift can be calculated mathematically, and then a pressure can be known which is exerted on the membrane here. The next one is the piezoelectric technology. As the name suggests, it uses the piezoelectric sensing element. Natural crystals such as quartz or ceramics are generally used. A thin membrane is attached to this crystal, and when under the pressure, the membrane deforms. The sensing element produces an equivalent output voltage. These kinds of pressure sensors are very rigid and can be used for the higher amount of pressures. The main drawback of these sensors is that they cannot be used for the static pressure measurements. Only the dynamic pressure measurements is achieved with these kinds of pressure sensors. Another type of the technology being used for the pressure sensor is the magnetic one. Here, the sensing element is the membrane which changes its magnetic field when it is subjected to a pressure or an external force. The another one which we are going to talk in detail is the piezo-resistive and capacitive technology. These are basically the MEMS-based pressure sensors, and in MEMS-based pressure sensors, these two technologies are widely used. Let's have a look at the first one, the capacitive technology. This technology uses the basic principle of the parallel plate capacitance, where a thin diaphragm is fabricated and which is movable, and then another reference diaphragm is fabricated at a distance of d. Whenever the movable diaphragm is under the pressure, it gets deformed, and the distance between the reference plate and this changes, and at the end, the capacitance changes as well. These kind of structures are fabricated into an array, as you can see here. There are reference arrays and sensor arrays. What does that mean? So the sensing cells have a flexible membrane that reacts to the pressure change. The reference cell has no flexible membrane, which is always the constant. So the reference cell always gives you a constant measurement of capacitance, and the flexible membrane gives you the measurement of the pressure as per the pressure applied. These arrays are formed into an Wheatstone bridge configuration, as you can see. So across the capacitance, this always stays the same, and the sensing capacitance changes as per the pressure applied. The benefit of this kind of structure is that the pressure measurement is more or less differential, and both the sensing and the reference cells are exposed to the same temperature changes. That is a big benefit, that the temperature does not have a large effect on the pressure measurement. Another benefit is that the sensor is more tolerant for a short-term overpressure. On the other hand, the sensor has a nonlinear output. Also, the low signal to noise ratio leads to a low dynamic range as well. Because it's a capacitive technology, it has some parasitic capacitance, and in order to eliminate the parasitic capacitance, it needs some more electronics. At the end, it is also difficult to manufacture because of these reasons. Next is the piezo-resistive technology. The piezo-resistive technology basically works on the principle of piezo-resistivity, which is change in electrical resistivity of a semiconductor or a metal due to applied stress, which is pressure, force, or some flow. The piezoresistors are doped on the thin membrane, the thin silicon membrane. This membrane is fabricated via a standard silicon etching process, where the silicon wafer is etched from the bottom to the top, and the desired thickness of the membrane is achieved with the help of the etch stop process. A benefit of this process is as well that we can achieve a very thin diaphragm, and the thinner the diaphragm, the more sensitive the pressure sensor can be. The piezoresistors are, as you see in here figure, are placed in a Western bridge configuration, same as what we saw for the capacitive sensors. Here, the capacitors are replaced with the resistors. When the pressure is exerted on the diaphragm, some of the some of the resistors are under the compression, and some of them are under tension. And this changes the resistance of the piezoresistors, which makes the bridge unbalanced, and it generates an output signal in terms of millivolts, which is directly proportional to the pressure exerted on top. Because we don't have any other circuitry alongside, this output is uncompensated and non-calibrated. For further pressure measurement, this output needs to be calibrated for the temperature as well. This piezoresistive technology has a high linearity, and also it's easy to produce. The drawback for this technology is that it is sensitive to temperature changes. So in the application where the temperature is changing rapidly, the pressure might not be the correct. The sensors from Würth Elektronik work on the piezoresistive technology. We will discuss this in some slides. Before moving forward, it is also important to know which kind of pressure sensor I need. Let's get back to the slide we saw previously about the types of pressure. Based on this, the pressure sensor is also in different types. The first one being the absolute pressure sensor, which measures the atmospheric pressure from the top, and as a reference, the vacuum is sealed during the fabrication. There is no outlet port on the other side. For a gauge pressure, you can see there is an inlet port for the other side to let the atmospheric pressure inside the cavity. Whenever pressure is exerted on the top, it measures with respect to the atmospheric pressure which is inlet from the other side. This is the gauge pressure sensor. The differential pressure sensor is very much similar to the gauge sensor. The only difference is here the reference pressure is also user defined. That means that user can connect two different pressure to this sensor and measure a difference between both of the pressure P1 and pressure P2. More or less, a differential pressure sensor is also a gauge sensor. When you open the port P2 to the air and let the atmospheric pressure in, the differential pressure sensor work as well as a gauge sensor. Another important aspect to consider is that what level of integration do I need for my pressure sensor solutions. There are different kinds of manufacturers who provide different kinds of pressure sensors from analog to digitals. Let's understand what they are actually. Here you see the MEMS sensing element, the piezoresistors in a Western bridge configuration. They are packaged, they are sold as a bare die or packet sensor die. Usually, these sensors provide the millivolt output, as we saw earlier. Since they are neither calibrated nor temperature compensated, additional signal processing needs to be implemented with the help of external circuits. There are also some sensors available with amplification. So with this MEMS die, an amplifier is added. These are called amplified pressure sensors. They are also analog usually, and sometimes they are also passively compensated. Passively compensated means that they are in fabrication once compensated at a particular temperature. So in order to use the sensor where there is a need of a dynamic change of temperature, the sensor must be recalibrated during the applications. The next one is the digital pressure sensors. The digital pressure sensors are much more complex than the previous what we talked about. They have an analog to digital converter. So the amplified signal is fed to the analog to digital converter and the signal is digitalized. And then they are sent to a digital signal processor unit, a small microcontroller on chip. This also has an onboard memory and filters. These kind of sensors provide usually fully compensated and fully calibrated output. The calibration parameters are also stored in the memory, and user also has the access to this controller, and he can change some of the modes during operation of the sensor. This means, for example, the user can turn on or turn off the filter of the sensor depending on his application requirements. The sensor comes with a dedicated interface unit where I2C, SPI, analog output are also available. The user can connect their microcontroller with them easily and then use the pressure data much faster. It is fully calibrated as well. That was the part of what level of integration today what we have in the sensors. The pressure sensors from Würth are all digital and fully compensated and fully calibrated. First, let's have a look at the absolute pressure sensor. As you see, the absolute pressure sensor, there is one inlet and the reference vacuum is sealed inside. This is the package from our absolute pressure sensor. The ASIC and the MEMS is mounted on top of the substrate. The ASIC contains all the multiplexer, analog to digital converter, and the microcontroller, as we saw in the previous slide in the ASIC. The MEMS is mounted on top. The MEMS has an inbuilt vacuum cavity for the reference and holes on top. MEMS, ASIC and substrate are wire bonded together, and the whole package is fully molded. The fully molded package provides increased robustness as well. On the surface, there are multiple vent holes, which exposes the air to the silicon membrane. Smaller holes reduces the contamination risk as well as improves dust and moisture resistance. One thing more to note here is that there are multiple vent holes available on top of the sensor. This means that even if some of the holes get blocked, the sensor can still measure the air pressure correctly. The block diagram, let's have a look at that. Here, block diagram, we have the same sensor bridge, which is the sensing element in the piston bridge configuration, which makes the MEMS element. It is then fed to the amplifier, so the raw data is then amplified and then multiplexed. There is as well a temperature sensor integrated on chip. Usually the temperature sensor is a diode. So the pressure and the temperature data are multiplexed and then converted into digital form. This data is fed to the digital logic which is the digital signal processing or the microcontroller, where the digital filtering takes place, and also the pressure is compensated for the temperature. The temperature sensor is placed as close as to the MEMS element so that the temperature error can be minimized. The whole unit makes the ASIC. The ASIC also has the registers and FIFO buffers where the pressure and temperature data are stored, and it can be read from the microcontroller via I2C interface. There is also a dedicated interrupt generator where the pressure interrupt can be generated from the user from the microcontroller when the pressure gets uh, below or above a specific user-defined pressure values. From the register, as mentioned, user can read all the pressure data which is fully calibrated. The sensors are calibrated at multiple temperature and pressure values, and these values are always stored in the on-chip memory of the sensor, and they are loaded every time when you restart or power up the device. Let's have a look at some key specs of the sensor. As mentioned, the sensor is fully molded in the 2 by 2 millimeter of very small footprint, a square C interface. The pressure range it can measure is from 260 millibar to 1260 millibar. If you see on the right hand side in the image, as you can see, the 1260 millibar range is almost below the sea level, because sea level pressure is around 1000 millibar. On the other hand, 260 millibar corresponds to almost 9,000 to 10,000 meters of altitude, where normally the flights fly. The pressure data is 24 bits of resolution, and the temperature data has 16 bits of resolution. Here, the temperature sensor also has another temperature sensor is not only used for the temperature compensation, but also the user has a possibility to read the temperature data from the device. The accuracy of the sensor is plus or minus 1 millibar, and the temperature sensor accuracy is plus or minus 1.5 Celsius. This is important where if the customer can use just one sensor in order to have also the temperature measurements. The sensor has a really low current consumption because the sensor can be put into the power down mode or a sleep mode when the data from the pressure sensor is no longer required. This saves a considerable amount of power as well. The sensor can be asked for the new data only when required, and rest of the time the sensor can be in the sleep mode. Because it works from 1.7 to 3.6 volts, it can be also used for the battery operated devices. The sensor also includes a inbuilt voltage regulator. Let's have a look at some of the features and settings of the sensor. There are two filters inside, of which one filter is always on, and the another filter is user dedicated. So user can turn on or off this filter based on his application. Here you can see the comparison of the filter turning on and turning off, where when filter is off, there is a considerable amount of noise, but the current consumption is much more lower. On the other hand, when the filter is turned on, the noise performance is largely improved, but at a smaller increase in current consumption. It should be also noted that in order to have a low noise mode enabled, it reduces the bandwidth and also reduces the output response time, because another filter needs also time to process the data. When in the lowest noise mode, the sensor can sense around 6 to 8 centimeter change of altitude. The sensor also comprises of a inbuilt FIFO memory buffer, which is a first in first out memory where data can be stored and read only once when needed. This is helpful to save more power, so the microcontroller does not have to pull for the data continuously, but on the other hand, the sensor stores the pressure data inside its inbuilt memory and then sends all the data at once to the microcontroller. The sensor, as mentioned previously, also has the programmable interrupt, where pressure low or pressure high events can be generated and the microcontroller can be alarmed. That was all from the absolute pressure sensor. I will move now with another pressure sensor, which is the differential pressure sensor. As you can see, the differential pressure sensor package looks a bit different from what we saw previously. It has two pressure ports on the top, P1 and P2, to let the two pressure inputs. The port P1 is on the top side of the MEMS sensing element. This directly exposes to the top side of the membrane. The port P2 has a inbuilt pneumatic channel which leads to the other side of the MEMS element. So this port P2 acts as a reference port. So user can measure the pressure difference between P1 and P2 effectively. The MEMS sensing element is placed on a ceramic substrate. Since silicon and ceramic have the same temperature coefficients, this significantly improves the mechanical stability of the sensor. And stresses in the sensor can be reduced because stress produced by the temperature differences can be minimalized. The sensor comes in the SMD package. Since the pneumatic channel enables that we put the both ports on the top side, there is no port on the bottom side. The sensor is a leadless SMD package. The edge castellation at the sides is also important to see if the soldering is done properly, and also enables the hand soldering process. The block diagram of the differential pressure sensor looks almost similar to what we saw previously. It again has the same piezo-resistive Wheatstone bridge as a sensing element. This differential pressure signal is then fed to the amplifier, and this signal is amplified and multiplexed with the temperature sensor. This sensor also comprises of a temperature sensor for the compensation of the pressure with different temperatures. The multiplexer transmits these signals from the MEMS cell and the temperature sensor to the ADC. The digital signal processing is done in the calibration controller, or the ASIC. The EEPROM is where the calibration data are stored and are loaded to calibrate the sensor, calibrate the raw data coming from the bridge. The serial interface is I2C for this sensor, so with the I2C interface, the pressure data can be read. The sensor also has an analog output. The analog output is not just the normal analog output, because there is a digital to analog converter which converts the digital pressure values to analog values, and this analog values is able use for the user available. So here it should be noted that the analog signal would also have some internal conversion time like the digital one, because the analog output is not purely analog but is amplified, digitized, compensated, and again converted back to the equivalent analog signal. So the key specs for the differential pressure sensors. We have the sensors in 5 different measurement range, being the lowest range being plus or minus 1 millibar. The medium range consists of plus or minus 10, plus or minus 100 millibar, and 0 to 1 bar. The highest range is from minus 1 bar to 10 bar. The three sensors plus or minus 1 bar, plus or minus 10 bar, and plus or minus 100 millibar are bidirectional sensors, which means that port P1 and port P2 can have either of the pressure. So port P1 can either have pressure larger than port P2, or port P2 can have pressure higher than port P1. It doesn't make sense, doesn't make difference. On the other hand, the remaining two sensors 0 to 1 bar and minus 1 to 10 bar are only calibrated in one direction. That means that port P1 must always be at higher pressure than port P2. The accuracy of the sensor, you can see here, this is the absolute accuracy, and which is compensated for the whole temperature range. The sensor works on a 5 volts. The 15-bit resolution is also valid for pressure as well as temperature data. And as mentioned, the I2C and analog interfaces are available for this sensor. So each sensor for each transfer function is individually calibrated. the temperature compensation is between 0 and 70 degrees Celsius. Another important thing is that the digital output is not ratiometric. What does this mean? The ratiometric means that the output changes with respect to the input changes of voltage. So when I have an input voltage change, my output also changes. This is not the case for the digital output, as it has a digital digital signal processor and also an on-chip voltage regulator. Here, I would like to go in the direction of the tube connections, as it is also widely demanded. So, because of the two ports on the top, the tubes can be easily connected to the sensors. The 2 mm diameter tubes can be directly connected to the sensor ports. However, at higher pressure, the direct connection is not recommended. That's why we provide our evaluation board with an extra pressure adapter and O-rings. The adapter can directly be mounted on top of the sensor, and it has also the barbed nozzles, to which standard 6 mm pipes can be connected. This significantly improves the mechanical stability. The pressure pneumatic tubes can be connected up to 10 bar. The pressure adapter also is helpful in order to reduce the stress on the solder joint. When the tubes are connected directly, the pressure pulses also make stress on the solder joints, and since the solder joints are not meant to withhold so high stress, it can get damaged. Also, the pressure adapter increases safety in case of leakage or in case of other emergency cases. In order for you to use the adapter in your application, if you need to modify it, the CAD files for this adapter are available on our website so that you can modify as per your needs. That was all from the two sensors. Now let's move forward with the application of these sensors. First is the application for the absolute pressure sensor. Altimeter is one of the most popular application for the absolute pressure sensors. Altimeter basically measures the height, because air pressure and altitude or the height have a relationship as mentioned in this figure. Here the temperature changes are not considered because of if we want to measure a height, the temperature changes are not so often seen. So we placed our sensor in a lift and measured the pressure. As you see, the change in altitude is recognized for each floors. Over here, however, you see some strange behavior. At this point, someone had entered the lift and sudden change of air pressure was seen. This resulted into some noise. This shows that how sensitive the pressure sensor is. This can be implemented in the indoor navigation or the floor detection. The sensor is also able to recognize each step, as we put the sensor on each step, and as you can see, each step was individually identified with a change in pressure. Moving forward with the application of the differential pressure sensor. HVAC is the most popular application for the differential pressure sensor, heating, ventilation, and air conditioning. It is used for the air filter monitoring, where, for example, air is flowing through a filter from right to left. When the filter is new or okay, then pressure P1 and pressure P2 would be almost similar. But when the filter gets clogged with the dirt, the pressure P1 increases significantly, and it can send a notice to the customer that it's time to change the filter. Same way, it can be used to control the ventilator or the fan. And also it can be used for the air pressure control of some laboratories or some clean rooms where constant air pressure is required. Here the sensor can be also used as a gauge configuration where port pressure P2 is always kept open to the air, and the air pressure inside the tube is always controlled with respect to the air pressure. Apart from this, there are many more applications. For example, in the drones to maintain the constant altitude, in the vacuum cleaners, the dust bag replacement, or the flow type detection for the smart vacuum cleaners, or the white goods, dishwashers, or washing machines. The absolute pressure sensor is also widely used in weather stations or GPS enhancement where the accuracy can be improved. The differential pressure sensor can also be used in the gas meters where a large or a high amount of leakage can be detected. At the end, I would like to mention our support. The sensors we provide have a long time availability, so that once you use the sensors in your design, it's not possible that they get discontinued or they are terminated after some years. So we provide a long time availability of all the sensors. All the sensors are for sure available ex-stock. Moreover, we provide direct design support and as well as technical support. Also, please have a look at our sensor portfolio where we have temperature sensor and 3-axis acceleration sensors. Further webinars are also planned for these for the more information. So that's all from my side. Thank you very much for your attention. Now I will ask some of your questions.
So, yeah, thank you, Ninat, for this great webinar. And now we would like to turn our attention to your questions and wait a little while until some questions have come in. In the meantime, I would like to draw your attention once again to the fact that in a few days, you will be able to view the webinar again on our website. After the webinar, we will also send you all documents in a separate email. So now we would like to answer some of your questions. And Ninat, I see the first question has come in. Ninat, can I use the differential pressure sensor for liquid or fluids?
Unfortunately not. The differential pressure sensor is only compatible with clean, dry and non-corrosive gases. The liquids will sure damage the sensor and the sensing element as well. However, small particles are allowed as far as they do not block the pneumatic channel. This might also have some effects on the accuracy as well. For the what kinds of gases to be used for this sensor, please refer to the user manual.
Okay, thank you, Ninat. The next question also arrived. What is the media compatibility for the pressure sensors?
As mentioned already for the differential pressure sensor, for the absolute pressure sensor, it is intended to be used to measure the air pressure. So it is also not waterproof, and it should be also only used for the measurement of the air pressure. And yeah.
Okay. So I see also the next question arrived. Ninat, how are sensor internal response time and output data rate related?
Yeah, as mentioned, that sensor requires some time in order to process the digital signal, to process the pressure data digitally and to compensate for the temperature. So, for example, let's say the internal response time of the sensor is 13 milliseconds, and I'm asking the new pressure data from the microcontroller every 5 milliseconds, then I get at least 3 times the same pressure data until the new pressure measurement is available. So when you ask for more, you ask the data at higher data rate, you are basically doing oversampling. You are not getting a new data, but you are reading the same data because internally sensor requires more time to process a new set of measurement.
So, Nina, thank you for these details. Yeah, I see. We also have the next question. Do you have kind of support for software, like software development kits?
Yeah, sure. We do provide the kind of software development kits for the programmers, where we have software independent drivers available, also with some examples. So the user can directly plug and play their sensor not just on the hardware side but also on the software side. With the help of these sample codes, you can directly check the first communication with your microcontroller and read out the first data of the pressure sensors.
So interesting. There are a lot of stuff. So
Yeah.
the next question, how do I get some samples?
In order to get the samples, you can contact one of our sales guys or our customer support on the online. Then if you leave the request for us, then one of our sales guys will contact you and get in touch with you regarding the samples.
Yeah, and I also can add here, if you have you don't have any email, just write at the email you see below at isis-webinar@we-online.com. So the next question that arrived. Do you offer some program examples and eval boards?
Yeah, exactly what I mentioned in the software development kit SDK. There are also not just the driver files, but also some of the example codes for the eval boards that you can directly plug and play.
Okay, so now it's the chance for some more questions. And yeah, there's the next one. Have you planned to extend sensor measurements range? I am actually looking for a minus 250 to plus 250 millibar range.
Unfortunately, as of now, we don't have the plans for the extended measurement range. What we have is plus or minus 100 millibar, and the other one is 0 to 1 bar.
Okay. So then we are looking for another questions. So the next question is, what is the connector on the evaluation board?
The evaluation board comes with the I2C connector, the 6-pin, and this is also compatible with our Ember Pi design kit, so that it can directly stacked up in our Ember Pi. And for the other evaluation, it also has the pin headers so that you can connect it to a breadboard and then do also evaluation with the each pin connection.
So yeah, the next question, Ninat, how big is the pressure sensor? So the dimensions of the sensor.
So the absolute pressure sensor is very small. It's 2 cross 2 millimeter. On the other hand, the differential pressure sensor is a bit bigger. It is 13 millimeter by 8 millimeter.
Okay, so you have to be careful. Don't lose them.
Yeah, sure.
So we are now looking for another question. So we need another minute. Okay, we see now the next question. What is the maximum height to measure with the absolute pressure sensor?
As mentioned, the pressure sensor's minimum measurement range is around 200. It's 260 millibars. So if you convert 260 millibar in the altitude at a nominal temperature of 15 or 25 degrees, it corresponds to around more than 9,000 meters. So for sure you can measure up to this height, which is the height at altitude at what the aircrafts fly.
So yeah, I think if there are no other questions, we are finished with our webinar. If there are any questions left, we will all answer them via email afterwards. So none of your questions will not be answered. So thank you very much for your attention, and I hope you enjoyed our webinar. Also, many thanks to you, Ninat, for this great webinar.
Thank you very much and have a nice evening.
Yeah, I hope we will hear us at our next webinar, and also from me, a nice evening. Goodbye.